Okay, in our last video, the first video on uniform circular motion, we discussed rotation angle. We talked about arc length. We also talked about angular velocity and tangential velocity. And so in this video, I'm going to start off by introducing the sort of last quantity that we need to sort of define before we're ready to talk about uniform circular motion sort of more generally. And that's going to be centripetal acceleration. Okay, and so what are we talking about when we're talking about centripetal acceleration? Well, let's think about what's happening as something as something has uniform circular motion, right? As some object is moving through a circular path here. Our velocity is changing all the time as it's moving like this. So I've drawn this little diagram down here already. And we can see that although the magnitudes of these velocities, the length of these vectors aren't changing, their direction is changing, right? So I have the magnitude of v1 is equal to the magnitude of v2 is just equal to the magnitude of v, which we'll just label some general v, right? Excuse me. But so the magnitudes aren't changing, but the direction is constantly changing, right? So it was pointing in this direction first, and then it's pointing in this direction after some delta t, some change in time. And so let's collect those two vectors, v1 and v2, and put them tail to tail. And if we do that as I did down here, we can see that we can construct a delta v, which is going to be a change in this velocity, and it's going to run from the head of v1 to the head of v2. And so it'll be defined by this equation here, which we can rearrange into this equation here, right? And so, sorry, I have a bit of a raspy throat today. I may have to pause my talking here and just cough for a moment, but bear with me while I continue here. So we can define this this delta v as we have here, right? So we have the equation here, and we have our drawing that's showing us what delta v is here. But we also know that we define acceleration as some change in velocity, some delta v, over some change in time, delta t, right? This is our old definition of acceleration. And so acceleration is just a change in velocity over a change in time, right? And this change in velocity that we have above, here and here, are happening over some change in time, right? So there's definitely some change in time as this object is rotating around its circular path, right? And so we can define centripetal acceleration as this quantity here. It's just going to be this delta v that we just defined above over the change in time over which it happens, right? So that's going to be a useful definition that we're going to use sort of repeatedly throughout this module. So that's an important equation. So I've started to box the important equations at this point. So those are the ones you're going to want to remember, and that I'll probably tabulate into a formula sheet for your use later on. Okay, so from the above drawing, we see that that delta v points radially inward, and so my drawing is not perfect here, but you can imagine that as you go around the circle, if we had this put sort of up into this diagram over here, then this delta v, no matter where we were moving around the circle, as we were adding different v1 and v2, different initial v and different final v, we would always find that the definition of delta v ends up with a vector that points radially inward. So wherever we are, it's going to be pointing radially inward. Okay, so we have the direction of our centripetal acceleration, of our AC here, but we don't have its magnitude yet. So we're going to take a look at finding the magnitude. And as I mentioned here, we could prove this fact about the pointing of AC inward radially all the time more rigorously, but for this course it's sufficient to just understand that it always points inward, and we don't really need to worry about proving that, okay? But what we are going to be interested in is finding the magnitude of our AC, of our centripetal acceleration. And so what I've done here is I've drawn two blown up versions of the diagrams from above. I put a little more detail into the first one here. And so this is just me zooming in on the circle. We can see that we still have our same V1 and V2 here. Our delta theta, our rotation angle is listed on the diagram here. We have both of our, well, we have our radius written in here. I've also added in delta S, which is our arc length, and I've added in this delta R, which is just a line connecting our two radii, right? And I've also shown here that the V1 and V2 make right angles with this radius because they're tangent to the circle, right? And so by looking at this, we can see that this delta theta that we have in this diagram here is actually the same as the delta theta we have in this diagram over here. Now I won't prove it. We could prove it a number of different ways. We could use similar triangles and a bunch of different constructions. We could also notice that as this delta theta over here goes through a full 2 pi revolutions, clearly this one would have to also. And so that shows us that they're actually going to be the same angle. But I'll leave that to you guys if you're interested in proving it. But for now, we'll just state that delta theta is actually that both of these angles are actually delta theta. Okay. And so since we know that delta theta is the same in both of these diagrams, and since we know that the magnitude of V2 and the magnitude of V1 are actually both just what we're going to call V, then through the use of similar triangles, we can see that it must be true that delta R over R is equal to delta V over V. Now let's take a look at the diagrams and see what that means. That means that this delta R over R has to be the same, has to be equal to, well, that ratio has to be equal to delta V over V, right? And that's just because of similar triangles. And if you would like to think about that more, maybe consider it later on, but for now we'll just move on and take that also as a fact, right? Let me just mute my microphone, clear my throat here for a second. Okay, and so now if we look more closely at that first zoomed in diagram that we have here, this diagram over here, we can imagine, and maybe specifically we want to look more closely at how delta R and delta S change in relation to one another, right? And specifically what happens as our rotation angle, as delta theta gets very small. So the smaller delta theta gets, the closer delta R gets to delta S. So you can imagine that we crank this angle back, and our delta R is getting closer and closer to delta S, and as we get to infinitesimally small delta thetas, our delta R really does go to delta S. They become the same thing as delta theta becomes infinitesimally small. So we could show this using calculus, but again, this is not a calculus-based course, so we're not going to go through the whole proof. We're just going to have to accept that it's true that as delta theta gets extremely small, delta R goes to delta S. And if that's the case, then this equation that we talked about just above, where delta R over R is equal to delta V over V, will then go to delta S over R is equal to delta V over V. And then at that point, we just take that equation, rearrange it in this form that we see here. Okay, so we have that there. And now if we divide both sides by delta t, which we're free to do if we'd like to, over the time that this happens, well, this side over here, this is just what we defined as our centripetal acceleration. Well, at least the magnitude of it for now. We know its direction is pointing radially inward. And what's this over here? Well, this is just our change in arc length over our change in time. Well, that is just our tangential velocity, which we've labeled as v, right? So if we clean that up, then, as I've done here, we get our second useful equation of. Oh, hold on one second. We get our second useful equation, which I have highlighted here, right? So this is another one that we're going to want to know. And finally, if we substitute in for v, our tangential velocity, using this relation here, which we came up with last video, which writes our tangential velocity in terms of the radius and the angular velocity, we can then write the final sort of useful form of the magnitude of our centripetal acceleration, and it can be written either as our tangential velocity squared over radius, or it can be written as radius times our angular velocity squared. Okay, so both of these are going to be very useful, and we're going to use those in a number of examples here in the next few videos. Okay, so that introduces centripetal acceleration. Let's do an example now using the centripetal acceleration. Okay, so we're interested in the magnitude of the centripetal acceleration that a car on a curve with a radius r equals 500 meters traveling at 25 meters per second is going to be experiencing, right? And so I have it over here, so I have the numbers, and let's take a look at that, right? So for part A, well, maybe I'll draw the problem here. So we have a curve. There's a car traveling on this curve. So this is like an above view, right? So the car has some tangential velocity in this direction. We know that v is equal to 25 meters per second. This curve that the car is on has a radius, and the radius is 500 meters, right? Okay, and we want to know what the centripetal acceleration that the car is experiencing is. So the car is going to be experiencing some centripetal acceleration pointing inward, and we want to know what the magnitude of AC is, right? And so how do we do that? Well, I mean, right away, if we look at our above equations, we know that that we can write our centripetal acceleration, or the magnitude of it, in those terms, or we could write it in these terms, right? And so which one works best for here? Well, we have both our tangential velocity and the radius, and so this means that AC is going to be equal to 25 squared over 500, and I have those numbers pre-calculated here. That is going to give us an AC equal to 1.25 meters per second squared, right? So the car is experiencing an acceleration of 1.25 meters per second squared pointing inwards on this turn as it's going around the turn, okay? And that would be the answer for part A. In part B, what are we looking for? How does this compare to gravitational acceleration? Okay, so we want to, basically when we're asked this question, how does it compare to gravitational acceleration, we're talking about how many g forces, or how many g this thing is experiencing as it's going through this turn. So really we can compare AC to g just in a ratio like this, and we just said that AC was 1.25 meters per second squared, and our g we know is 9.8 meters per second squared. And so if we do that division, we're going to find this is 0.13. And so what does this tell us? Well, this tells us that AC is actually 0.13 g. Okay, and so that would be the answer to that one. Okay, so what do we have up next here? Well, if we have a centripetal acceleration, anywhere that we see an acceleration because of Newton's second law, because of F equals ma, we should be expecting that if there is an acceleration, well, we should expect to see a force as well, right? So we're going to talk about the centripetal force here, and right away, I mean, we know that AC points in the direction of radially inward, right? Well, I won't write it here because I have it written just down below. But AC points radially inward, and so F will also point radially inward. And as far as the magnitude of our FC, our centripetal acceleration, well, we know we know that well, we just spent a bunch of time calculating an expression for what AC is, and AC is going to lead us to FC just by multiplying it by m, right? So simply we just take those expressions that we had above. We just take AC equals v squared over r equals, oops, that's a terrible r, v squared over r equals r omega squared, and we just hit them with m, right? So it's just going to be m, and it just leads us to this equation that we have here. And this is the two expressions that we're going to need for the magnitude of our centripetal force. Okay, and we'll use this in an example in a second, but I just want to point out a quick thing here. So any force, any net force, and it's really this first sentence that I have here. Any net force causing uniform circular motion is called a centripetal force. So what would be a centripetal force? Well, if we think about our above example, and we're going to go into this example again here, talking about forces, what would be the force causing the centripetal acceleration here? Well, in this case, it would be the friction of the tires on the road, right? The friction of the tires on the road are what's keeping this thing in this curved path. If there was no friction with the between the tires and the road, well, this thing would just start skating off the road here in this direction, in the direction of the tangential velocity, right? So the force keeping it in this uniform circular motion is the centripetal force, right? And another example would be, let's say you had a mass on a string. Say I have a person standing here with a mass on a string, and they're swinging this mass on a string around in a circle above their head, right? So they have a string, some mass here, and this thing is just whipping around, sort of like a helicopter, kind of above them, right? So what's the force that's keeping this mass traveling in this uniform circular motion? Well, it's the tension. It's the tension in the rope or the cable or whatever it is that's keeping this thing going. So in this case, T would be our centripetal force, right? And we're going to take another look at an example of this here in a second. Actually, maybe I should have left that. Okay. All right. So let's go down and take a look at our last example for this video. So in this example, we want to know what the coefficient of static friction is that car tires are going to need on a flat curve if the mass of the car is 900 kilograms and it's moving at 25 meters per second around a curve with radius 500 meters, right? So it's basically the same curve from above. We've given the mass of the car at 900 kilograms, and we want to know what mu sub s, what coefficient of static friction we need so that this car just stays in the curve. Okay. And so let's take a look at what's going on here. Well, from our should I redraw it? Yeah, I'll just redraw it here. So from our discussion just a moment ago, we know let me just quickly draw this here. We know that other forces are going to act for our centripetal force, right? In this case, like I said above, our force of static friction is going to be our centripetal force, right? And so because that's the case, we can start right away from this equation. Well, we know that maybe I'll write down what we know here first before I get into that. So we have m at 900 kilograms. We have v at 25 meters per second. We have r at 500 meters. We know that our force of static friction is going to be what's providing our centripetal force. But we know that we can write from this equation. We know that we can write our force of static friction as mu s times the normal force, and we're going to find it useful. Well, maybe I'll write both versions. We know that we can write Fc as mv squared over r, or we could write it as mr omega squared. But because we have v, we're going to want to use this version of it, right? And so from this equation here, we'll call this A, then A implies that mv squared over r is actually equal to mu s n. But we need the normal force, right? We don't know what the normal force is. What is the normal force here? Well, the normal force is going to be the force pointing up out of the page here, keeping the car from sinking into the road, right? So let's take a look at what's going on in the vertical direction. So in the vertical direction, Newton's second law tells us that F net is equal to the mass times the acceleration in that vertical direction. Well, there is no acceleration in that vertical direction, and we have the normal force acting in the positive vertical direction, so upward out of the page, and we have the force of gravity acting in the negative direction, right? And so this tells us that N equals Fg, and we know that Fg is just mg, so N is equal to mass times our gravitational acceleration. And so we can now substitute this, we'll call this B, this equation here, and we can now substitute this back into B. So B then tells us that mv squared over r is equal to mu s times mg. And let's keep in mind what we're looking for here. We want to find this mu sub s. We want to find this coefficient of static friction, and so we want to isolate it. And if we do that, we end up with mu s equals mv squared over r mg. We cancel out these m's, and this is just v squared over rg. And we can put numbers to it now, right? We know what the tangential velocity is, we know what the radius is, we know what the gravitational acceleration is, and so mu s is equal to 25 squared over 500 times 9.8. And I have that calculated over here. If we do that calculation, we find that mu sub s is equal to 0.13. And so this is the coefficient of static friction that we need for the tires and the road to have, so that this car remains on this curved path, right? And I should point something out here. You see here in the problem where we say a flat curve. So a flat curve simply means that this curve is flat in the plane of the paper, right? Like it's not a banked curve. You can imagine that like the whole curve happens in the plane of the paper. There's no lip to the curve that's coming up. Like this side of the curve is not higher up, like raising out of the paper, and this side is not lower down and going into the paper, right? So it's a flat curve in 2D. We will look at examples later where the curve is banked, so there's actually an angle formed in the curve, but we'll talk more about that in future videos. So I'll probably just leave that discussion for the next video, and we'll leave that here.